All right, so up next is a lot of math and talking about the three bounds that we discussed in lecture, which is essentially the big O bound, this one right here, and this one is big omega, and this one is called big theta. All right, so essentially what big O means is that it is an upper bound to how quickly a function grows, and big omega is a lower bound and big theta is a top bound. It's easier to visualize it this way. For example, here O of n log n, any function that is upper bounded by n log n is part of O n log n. Inversely, any function that is lower bounded by n log n, or rather some multiple of n log n, is a part of big omega n log n. So then, how do we get to big theta of some function? Well, it turns out that it has to be both big O of the function and big omega of the function. In essence, when you look at the graph, f right here will sort of be squeezed between the two g's. We'll get to an example where it becomes clearer in just a minute. All right, so right now we're going to be doing 2C, D, and E, which is just a true-false question. So first of all, we have 2C. If a function is in big omega of n, then it could also be in O n squared. So let's first discuss what big omega of n means for our function. Well, it means that our function has to grow at least as fast as n. For example, a function n would be just as fast as n, but n squared would be faster than n, so they would both be valid functions to be within omega of n. What does big O of n squared mean for our function? Well, it's the inverse. It means that our function will grow at most as fast as n squared. For example, a proposed function could be n squared, where n squared is as fast as n squared. But let's say a function like n3, that wouldn't be an O of n squared because that is faster than n squared. All right, so in order to visualize this, we need to sort of propose a function that is in omega of n and also in O of n squared, because that would prove that this statement is valid. So I'm going to open a Desmos link right here. We'll just wait for it to load real quick. So our proposed function is this black function right here. All right, it's y equal n to the power of 1.5. And notice here, the first thing that I want to prove is that that function is in big omega of n. So I pick n multiplied by some constant, which in this case I chose 0.1. And you'll notice that after the point 0, my black function here, my proposed function, is always going to be lower bounded by this green function, which is a multiple of n, right? And then so that means that yes, indeed, y equal n to the power of 1.5 is in omega of n. So now we just have to prove the other way around. So we want to prove that our function can be upper bounded by n squared. And so I just chose y equal n squared. And you'll see that this red function up to infinity is always going to be an upper bound to this black function, which means that yes, indeed, our black function is upper bounded by n squared, which means that our function y equal n to the power of 1.5 is big O of n squared. So we found a function that is big omega of n and big O of n squared, which means that this statement is true. All right. Next up, we have this statement: if a function is in theta of n, then it could also be O of n squared. So first of all, what does it mean for our function to be big theta of n? It means that it's tightly bound by n, right? And it's sort of this squeezing method I'll be showing in just a minute. And same thing as before, O of n squared means that our function grows at most as fast as O of n squared, as n squared rather. So here's the Desmos link that I'll just open up. All right, so first of all, my proposed function is this red function right here, y equal n. So we wanted to check if this function is in big theta of n. And to do that, we need to have two multiples of n that in the end will squeeze this red function. What that means is that it'll have something as a lower bound and something as an upper bound. So in this case, I have 1.1n as a purple line here, and I have 0.9n as the blue line right here. And you can see that those two lines, which are a multiple of n, is actually squeezing our proposed function y equal n, which means that n is in big theta of n. Now the other thing that we have to prove is that our function y equal n is in O of n squared, which means it has to be lower bounded by n squared. And lo and behold, if I just use y equal n squared, after this point y, this black function, which is n squared, will always be an upper bound to our proposed red function, which means that yes, indeed, n is upper bounded by n squared, and n is in O of n squared. So this turns out to be true as well. All right. Our next one would be, if a function is in big omega of n, then it is always O of n. So what does big omega of n mean for our function? It means that our function has to grow at least as fast as n. And this one means that it'll grow as slow or slower than n, right? So if we find a function that is in big omega of n, but not in O of n, it means that this statement is false. And that's what I'm trying to prove with this Desmos link. So first of all, I want to prove that a function is in big omega of n, which means that it will always be lower bounded by some multiple of n. So right here, I have my proposed function is y equal n squared. And I can see if I put y equal n, which is a multiple of n, this blue function will always be lower bounded. This red function will always be lower bounded by this blue function. And what that means is that n squared is in big omega of n. Now, the other thing that we want to sort of check, like, will this function be in O of n as well? So I have to find some c such that this blue function will be an upper bound for the red function towards infinity. And it turns out that it's actually impossible to do that. For example, if I set c equals n over here, you'll see that after this point, the red function becomes an upper bound to the lower function. Otherwise, and it doesn't matter like how big your c becomes, it turns out that it's simply not possible. And this means that our function n squared is not in big O of n, which means that we found a function n squared that is in big omega of n, but not in big O of n, which means that this statement is false.